After the development of Bohr's model, the concept of the wave-like nature in addition to the particle-like nature of energy from electromagnetic radiation became more mainstream. This was due to different experiments showing the radiation behaving like particles or waves. Then the idea struck Louis de Broglie, yes, matter acts like particles, but what if it could also act like a wave? He started first by applying this theory to electrons and stated that since the electrons that move around a nucleus of atoms behave like waves, they therefore have a wavelength. This solidified into an equation where wavelength lambda equals Planck's constant h divided by mass times velocity mv, where mass times velocity is defined as momentum. Therefore, any matter, such as a baseball that is moving, has a wavelength, but due to the mass of most objects, the wavelength is so minuscule that it's imperceptible. Since matter also has wave-like behavior, physicists could calculate with great accuracy the position, direction of motion, and speed at any instant of moving matter. Then Werner Heisenberg enters the arena. His uncertainty principle asserts that the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. He went on to prove it with a straightforward equation. The equation is delta x, the uncertainty in position, times delta mv, the uncertainty in momentum, is greater than or equal to Planck's constant divided by 4 pi. I won't go into the derivation for this equation since I'm not a theoretical physicist, but if you plug in the numbers relating to the electrons of a hydrogen atom, you get the uncertainty of the position of the electrons that is 10 times larger than the diameter of the hydrogen atom. Therefore, we have no idea where it is. We can just give the probabilities of where it might be. However, the math only comes out like this with extremely small pieces of matter because these effects become negligible at larger scales. The probability of finding an electron's location was further transformed with Erwin Schrödinger's wave equation, later known as Schrödinger's equation, which treats electrons as entities possessing both wave-like and particle-like characteristics and laid the groundwork for quantum mechanics. While Schrödinger's equation is mathematically complex, its application to the hydrogen atom revealed profound insights into electron positions at allowed quantum levels. Unlike Niels Bohr model, which depicted electrons orbiting the nucleus in fixed paths, Schrödinger's approach suggests that electrons occupy three-dimensional spaces known as orbitals. These orbitals represent probabilities rather than definite paths, introducing the concept of electron density distribution. In this model, areas with denser dots indicate higher probabilities of locating an electron, shifting from predicting exact locations to calculating likelihoods. Thank you for watching, and I hope these explanations help. If you have any further questions, feel free to ask, and if you found this video helpful, please like, subscribe, and let people know about the channel because it really does help spread the knowledge. Based on what you learned, think about the following questions. How did Louis de Broglie's hypothesis about the wave-like properties of electrons contribute to the development of quantum mechanics? How does solving Schrödinger's equation differ from Bohr's model of the atom in terms of describing the behavior of electrons around the nucleus? He extended the wave-particle duality concept from light to all matter, including electrons. Bohr's model gives us a simple fixed path for electrons, while Schrödinger's equation provides a complex probabilistic view of where electrons can be.